Massive stones fit together so perfectly that not even a blade of grass can slip between them. This is the work of South America's mysterious engineers, ancient builders who left behind architectural marvels, but no evidence of the tools they used. An early explorer described it perfectly, saying it was as if the stones were softened and molded by hand. By the end of this journey, you will understand why this technological disappearance forces us to rewrite history. How did they carve mountains with such impossible precision? And what happened to the advanced instruments that must have existed? What does true innovation actually look like when all its physical traces vanish high in the Andes? Mountains themselves were reshaped by human hands. Across a vast timeline, from the enigmatic Chavín over 3,000 years ago to the mighty Inca Empire centuries later, a series of cultures achieved the impossible. They built cities from solid rock without the use of metal tools, without the wheel, and often in breathtaking isolation. This was not the work of a single lost civilization, but a recurring theme of genius across pre-Columbian South America. The sophistication we see at these sites seems to appear suddenly, fully formed in the archaeological record. Expert archaeologist Dr. Maria Flores observes that what we find defies conventional explanations. The sheer perfection suggests tools far beyond the simple stone hammers and bronze chisels we have found in their ruins. From the highlands of Peru to the plains of Bolivia, the pattern repeats itself. Why did these distinct cultures, separated by time and distance, all gravitate toward such monumental and precise stonework? It speaks to a deep understanding of materials, a physics of stone that we are only beginning to comprehend. This widespread mastery points to a technological enigma that challenges our very timeline of innovation. It forces a difficult question. What does true progress look like when it leaves behind magnificent ruins but hides the very instruments of its creation? The answers are carved into the walls of specific, jaw-dropping sites where the mystery becomes undeniable. These zigzagging ramparts near Cusco are a symphony in stone, a fortress of interlocking blocks so immense they seem to defy gravity itself. The most colossal stones here are estimated to weigh 120 tons, yet they are fitted together with a jeweler's precision. This is polygonal masonry at its most advanced, where each block is a unique, multi-angled puzzle piece that locks perfectly with its neighbors. The joints are so tight that for centuries people have said not even a razor blade can be inserted between them. This was not merely an aesthetic choice, it was a profound feat of engineering genius. The irregular, interlocking shapes make the walls incredibly resistant to earthquakes. When the ground shakes, the stones in a Sacsayhuaman wall shift and settle, then lock back into place, rather than cracking and collapsing like a rigid, rectangular wall would. The builders understood the forces of their world on a deep, intuitive level. How they achieved this is a puzzle that has baffled researchers for generations. How were stones of such staggering size quarried from distant sites? The Incas had no iron or steel, only stone hammers and bronze chisels, tools that seem laughably inadequate for such a task. How were these multi-ton blocks transported over miles of rugged terrain without the wheel or large draft animals? Theories suggest they used log rollers, earthen ramps, and immense human labor, yet the exact methods remain speculative. Then there is the most tantalizing mystery of all, the cutting and fitting. The surfaces are not just flat, they are subtly curved and perfectly mated. Some researchers have proposed a controversial idea that the builders possessed a forgotten plant-based substance or geological knowledge that could temporarily soften the stone, making it malleable like clay. This would explain the flowing, molded appearance of the rock and the impossible seams. Local Quechua legends seem to support this, telling of a time when the very rocks became obedient, losing their hardness at the command of the builders. This was not random construction, it was a calculated design that reached for the heavens. The walls and prominent stone towers are aligned with celestial events, tracking the solstices and the movements of the stars. Sacsayhuaman was more than a fortress, it was a cosmic clock and a temple, a physical manifestation of a culture that saw no separation between engineering, astronomy, and spirituality. The perfection we witness here forces a single, haunting question. What kind of knowledge, what sophisticated tools or techniques could possibly produce such a masterpiece, only to vanish so completely from the historical record? But if the walls of Sacsayhuaman represent a symphony, then the stones of Puma Punku are a complex mathematical equation carved directly into the earth. On the windswept Bolivian Altiplano, this site shatters every conventional understanding of ancient construction. You are not looking at roughly hewn megaliths, but at a collection of geometric nightmares or perhaps dreams rendered in stone. The most famous components are the H-blocks, massive and precisely cut from a hard volcanic rock called andesite. Each one is an identical interlocking piece, featuring flawless 90-degree angles and grooves of a consistent depth and width, as if they were all stamped from the same giant industrial press. The sheer repetition of these perfect forms suggests a system of modular construction, a kind of ancient prefabrication where identical parts could be assembled and reassembled with the ease of a modern building set. Yet the true mystery deepens when you examine the smaller details. Across the shattered landscape of red sandstone and andesite slabs, you find evidence of a technology that seems to leap forward in time. There are drill holes bored with such consistent diameter and perfect circularity that they appear machined. Some stones feature intricate channels and notches cut with a sharp, unwavering precision, as if made by a diamond-tipped saw. The surface finishes on many of these blocks are unnervingly smooth, a quality that is incredibly difficult to achieve on such a hard material, especially with the primitive tools archaeologists attribute to the Tiwanaku culture. This was the people who built here, a sophisticated society that thrived for centuries before vanishing around the year 1000 AD, taking every secret of their manufacturing process with them into history. The silence they left behind is deafening. As engineer Dr. James Kensington notes, the tolerances and surface finishes at Puma Punku suggest the use of machine tools, yet we find no evidence of such technology in the archaeological record. The andesite itself is a formidable challenge, a stone so hard that shaping it with stone or bronze tools would be a labor of immense, almost unimaginable difficulty. How did they cut it? How did they polish it to such a reflective sheen? The geometric perfection of the blocks speaks to a deep mathematical understanding, a knowledge of advanced proportions and measurement that allowed for this incredible uniformity. What manufacturing process could possibly create such perfect stonework, leaving behind no tool marks we can recognize and no trace of the factories or workshops that must have existed? The stones stand as a silent, unanswered question, a puzzle that challenges not just how they were built, but why the very knowledge required to build them was so completely erased from the world. The journey from quarry to temple at Ollantaytambo presents a physics problem of staggering proportions. Here, the builders did not just shape a mountain, they commanded it to cross a valley. The fortress walls are constructed from massive blocks of distinct pink granite, a stone quarried from a mountainside several kilometers away on the other side of the fast-flowing Urubamba River. Each of these giants weighs approximately 50 tons, the equivalent of a herd of adult elephants, and they were moved across impossible terrain. The logistical nightmare is absolute. How do you transport dozens of these colossal stones down one steep mountain slope, across a raging river, and then up another slope to their final position, hundreds of meters above the valley floor, all without wheels, pulleys, or draft animals? The silence in the archaeological record is profound. We find no remains of the massive ramps, no traces of the specialized roads that such an operation would demand. The path they took is a ghost, visible only in the finished work. At the quarry site itself, clues are frozen in time. Unfinished blocks, still attached to the living rock, show how the stone was initially extracted. Workers likely hammered wooden wedges into natural fissures, then soaked the wood with water until it expanded, prying the block free with a percussive pop. This was the first step in a process that becomes increasingly mysterious with every meter of travel. Archaeologists propose that once free, the blocks were likely dragged on log rollers or slid on lubricated earthen causeways, a task requiring the coordinated labor of hundreds, if not thousands, of people. They would have had to construct a temporary bridge or causeway across the river, a feat of engineering in itself. Yet even these practical theories strain under the weight of the challenge. The sheer physical effort and the precision of coordination required to navigate such a route without a single block being shattered or lost. This is where local oral history offers a different perspective, whispering of a forgotten science. Quechua traditions speak of the ancestors, the Hatun runners, who possessed a sacred knowledge that allowed them to make the stones light, to command them to move through the air with the sound of a trumpet. While we might dismiss this as myth, it points toward a profound truth. The people who accomplished this may have understood principles of physics, of resonance and acoustic levitation, that we are only now beginning to explore in laboratories. The final insult to our modern understanding is the wall of the Sun Temple itself. Here, the transported granite blocks are fitted together with the same impossible precision seen at other sites, but with a peculiar addition. Several stones feature strange, protruding knobs known as bosses. These were not handles as they are often crudely called. Their function remains debated. Some suggest they were anchoring points for ropes during construction, while others propose they had a deeper, ceremonial purpose. Their presence on these perfectly finished surfaces is a final, cryptic signature from the engineers. The entire endeavor, from quarry to final placement, represents a symphony of logistics, geology, and social organization that we can scarcely comprehend. It forces us to ask not how they managed this with simple tools, but whether our definition of what constitutes a tool is simply too narrow. Deep beneath the earth at Chavín de Huántar, a different kind of engineering genius unfolds, one not of colossal weight but of controlled flow. This is not a fortress reaching for the sky, but a labyrinth designed to channel water, sound, and human experience through a network of stone-lined galleries that have remained dry and functional for over 2,500 years. While the Inca were building their empire, the Chavín civilization had already mastered subterranean engineering a millennium and a half earlier. Their entire complex is a testament to a profound understanding of hydrodynamics, the science of how water moves. The main plaza, for instance, was built with a sophisticated underground drainage system so effective that it has prevented flooding from torrential rains for centuries. But the water channels were more than just practical. Carefully engineered canals were designed to interact with flowing water, creating specific roaring and rushing sounds that echoed through the stone corridors during ceremonies. This was hydraulic engineering fused with acoustic design, a way to use the physics of liquid and sound to create a powerful, multi-sensory ritual experience. Archaeologist Dr. Roberto Chavez observes that the builders of Chavín demonstrated engineering knowledge that seems anachronistic for their time period, particularly in hydraulics and acoustics. This mastery is carved in stone at the very heart of the complex. Here lies the lanzon, a towering, blade-like monolith of white granite, intricately sculpted with a complex deity figure. To carve such detailed iconography into one of the hardest stones on Earth without metal tools represents a technical puzzle as deep as any at Puma Punku. What tools allowed for this precision, and how did they achieve such smooth, polished finishes in the cramped, dark confines of an underground gallery? The entire site was also an astronomical observatory, with architectural features aligned to solstices and equinoxes, channeling shafts of light into the dark depths at precise moments. This integration of astronomy, hydrology, and stonework reveals a long-term, multi-generational plan, a vision executed with mathematical certainty. The technological sophistication at Chavín, appearing so early in the timeline, forces a profound question about the origins of this knowledge. Was it developed in isolation, or does it point to an even older, as yet undiscovered, wellspring of engineering wisdom in the Americas? High above the desert floor, a monkey with a coiled tail stretches across the earth, its massive form only coherent from the vantage point of the sky. This is the realm of the Nazca, where the canvas is the arid pampa itself, and the art is etched into the landscape on a scale that defies human perspective. For nearly 2,000 years, these immense geoglyphs have waited, their straight lines, perfect triangles, and sprawling animal figures preserved in the dry climate. The creators of these lines never saw their work from above, yet they executed designs with a mathematical precision that would challenge modern engineers. How do you plot a straight line that runs perfectly true for over 10 kilometers across uneven terrain, using only the technology of the 1st century? The answer lies in a mastery of surveying that seems impossibly advanced. Archaeologists have found simple stakes at the ends of some lines, suggesting the Nazca used cordage and posts to mark their path. But this basic toolkit hardly explains the breathtaking accuracy. Cartographer Dr. Elena Mendez observes that the precision of the Nazca lines suggests the use of sophisticated surveying instruments, yet we have found only simple stakes and cords at the sites. To maintain such minimal deviation over vast distances, the Nazca must have employed a form of triangulation, using fixed points on the horizon like distant mountain peaks as their guides. They understood geometry on a grand scale, creating perfect spirals and complex biomorphic figures through an intricate understanding of proportions and ratios. The famous hummingbird, the spider, the astronaut, as some call it, each one is a testament to an ability to scale up a small model into a gigantic earthwork without distorting its fundamental symmetry. This was not random scraping, it was a calculated, large-scale architectural project. The technique itself was deceptively simple. The Nazca workers removed the dark, sun-baked surface stones to reveal the lighter-colored sand beneath. The stark contrast created the lines, and the dry, windless environment of the desert has acted as a perfect preservative for centuries. But the true mystery is not just the how, but the why. What was the purpose of this immense undertaking? Some researchers propose the lines formed a giant astronomical calendar, with certain alignments pointing to celestial events like the solstices. Others believe they were sacred pathways, walked during rituals to petition the gods for water in this arid land. The very act of their creation, a communal effort requiring precise coordination and shared knowledge, might have been the central point. This leads us back to the vanishing act of their technology. The stakes and cords we have found feel inadequate for the task. Where are the specialized tools for large-scale drafting, the devices for ensuring constant angles and unerring straightness? The knowledge system itself was the most sophisticated tool, a living technology of measurement and spatial awareness that was passed down through generations. When the Nazca culture faded, that intricate knowledge, that specialized toolkit of the mind, may have dissolved back into the desert sands, leaving behind only its immense and silent questions etched upon the earth. The most fundamental mystery begins with a simple, unsettling absence. Where are the tools, at sites shaped from granite and andesite, stone so hard it can spark? We find no trace of the metal implements needed for such work. This is our first vanished tool mystery, the case of the missing metal. We know these cultures possessed sophisticated metallurgy, creating magnificent objects in gold, silver, and copper for royalty and ritual. Yet at the quarries and construction sites, the evidence for metal tools is shockingly scarce. The few copper and bronze chisels and crowbars that have been found appear almost delicate when set against the monumental stonework they were supposedly used to create. Metallurgist Dr. Carlos Rivera puts it plainly, stating that the metal alloys available to these cultures simply were not hard enough to work the stones we see shaped with such perfection. Copper is a relatively soft metal. A copper chisel used to pound on granite would blunt and deform after just a few strikes, becoming useless long before it could make any significant progress on carving a precise joint or a smooth, curved surface. This creates a glaring technological contradiction. The hardest stones, the ones that should have been most resistant to their available tools, display the finest and most intricate work. The andesite at Puma Punku, for instance, is covered in those machined-like grooves and perfect drill holes, a task that would have shattered and destroyed any copper tool attempting it. Experimental archaeologists have tried for decades to replicate this stonework using only period-appropriate tools. Teams of researchers have used stone hammers, copper chisels, and sand for abrasion. While they can eventually shape a block, their results never achieve the flawless seams, the mirror-like polish, or the complex geometries of the originals. The process is agonizingly slow, and the finished product, while impressive to the modern eye, lacks the supernatural precision that defines these ancient sites. There is another telling clue, or rather, a lack of one. On the exquisitely finished surfaces of the stones themselves, we find no tool marks that correspond to the use of metal implements. There are no telltale gouges from chisels, no parallel scrape marks from saws. The surfaces are often unnervingly clean, as if the stone was worked in a single, fluid process rather than through millions of percussive strikes. This silence is deafening. It suggests that either the tools used were so advanced they left no recognizable marks, or that the entire methodology was fundamentally different from anything we have considered. So if metal tools were not the primary instruments, what was? Did they possess a secret formula for a hardened alloy, a type of bronze with unknown properties that has since corroded away entirely? Or did they rely on something entirely different, a knowledge of stone itself that allowed them to work it not by force, but by understanding its fundamental nature? The absence of these essential tools is not just an archaeological footnote. It is a gaping hole in our historical narrative, forcing us to question what we think we know about the very process of creation. The stones themselves bear silent witness to a second, even more baffling disappearance. Beyond the missing metal tools lies the mystery of the cutting systems, the very instruments that would have sliced through granite and andesite with the clean, surgical precision we observe. Look closely at a block from Puma Punku. You are not seeing rough, fractured edges. You are seeing what appear to be clean, straight cuts, surfaces so flat and smooth they seem to have been made by a massive, powered saw. The striation patterns left on some stones are the only clue, faint parallel lines that suggest a back and forth motion, a blade drawn across the stone again and again. This points directly to the use of saws, but not saws as we know them made of steel. These would have been slab saws, likely made of wood or copper, that used a mysterious abrasive compound to do the actual cutting. The saw itself was just a delivery system for a substance hard enough to grind down volcanic rock. So what was this magical abrasive? Experimental archaeologists have tried everything. Quartz sand is a common suggestion as it is harder than many stones, but tests show that using quartz sand with a copper blade is an agonizingly slow process, incapable of producing the deep, flawless cuts seen at these sites. Some researchers have proposed the use of diamond dust, as diamonds are the hardest natural material known. Could these ancient engineers have discovered and harnessed crushed diamonds, creating a super abrasive slurry? It is a tantalizing thought, but one for which there is no archaeological evidence whatsoever. No containers of diamond dust, no workshops for its production. Not even a single diamond tool has ever been found at any of these sites. The straight cuts present another layer of the puzzle. How did they maintain a perfectly straight line over a distance of several meters, ensuring the cut did not wander or bow? This requires not just a sharp abrasive, but a rigid guiding system, a kind of track or jig that would keep the saw on its true path. We find no remnants of these guiding frameworks, no stone rails or wooden fixtures. Then there is the evidence of drilling. Scattered across these sites are stones with perfectly cylindrical holes bored into them. The holes are uniform in diameter, with clean, parallel sides and a consistent spiral groove on the interior, a mark that suggests a drill bit was used with a consistent feed rate and pressure. To achieve this in hard stone with a hand-powered drill and a simple abrasive is a feat of immense skill and patience. Tool replication expert Dr. Amanda Chen observes that the cut marks suggest the use of advanced lapidary techniques that we would not expect to see for another 1,000 years. This statement cuts to the heart of the mystery. The technology implied by the stonework seems to leapfrog the known capabilities of the time. Perhaps the most telling absence of all is the lack of workshops. A technology this sophisticated would require centers for manufacturing the tools, for sharpening them, for mixing the abrasive compounds. These would not be small, hidden spaces. They would be industrial sites filled with debris, worn-out tools, and the residue of production. Yet the archaeological record is silent. It is as if the tools were used and then vanished into thin air, or were so specialized that they were collected and hidden away after their work was done. What cutting system could possibly explain the evidence left in the stone, while leaving no trace of itself behind? The answer might force us to reconsider the very nature of ancient innovation. These stones did not simply arrive at their destinations. They were coaxed, cajoled, and commanded across landscapes that would challenge a modern truck. The third great vanished tool mystery lies not in the cutting or the carving, but in the colossal effort of movement and placement. How did ancient engineers transport 100-ton stones across miles of river valleys and up steep mountain slopes, then hoist them into position with such exacting care? The physical evidence for the machines that must have done this work is utterly missing. We find no wheels, no pulleys, no remnants of massive cranes or complex lever systems. The conventional explanations begin with log rollers. The idea is simple enough. Teams of workers would lay down a track of logs, lever a stone onto it, and then pull the stone forward, with workers constantly moving the logs from the back to the front. This method works in theory, but it falters when faced with the reality of the terrain. The path from the Ollantaytambo quarry, for instance, descends a sharp slope, crosses a river, and then ascends again. On a steep decline, a 50-ton block on log rollers becomes an uncontrollable, crushing weight, threatening to pulverize the logs and overrun the workers pulling it. For ascending the other side, the friction would be immense, requiring a force equivalent to hundreds of people pulling in perfect unison. Another theory involves sledges on lubricated causeways. Here, a massive wooden sledge carries the stone, sliding on a path made slick with mud or some other substance. This reduces friction, but it introduces new problems. The sledge itself would be a tremendous engineering project, and the path would need to be meticulously prepared and constantly maintained. For stones weighing up to 200 tons, the ground pressure would be immense, likely causing the sledge to sink into even a prepared track. The logistical coordination required is almost beyond comprehension. We are talking about orchestrating hundreds, perhaps thousands of laborers, not just for muscle, but for a carefully choreographed ballet of movement. They needed precise communication, a shared understanding of physics, and a system for managing ropes, levers, and pathways. There is no room for error. A single misstep, a snapped rope, a crumbling ramp, and the project could end in catastrophe. Engineering historian Dr. Benjamin Carter observes that the transportation achievements alone would be impressive with modern equipment. With primitive technology, they seem almost miraculous. Once a stone arrived at the construction site, an even finer challenge began: the lift. How do you raise a 100-ton block 20 feet into the air and then lower it onto its neighbors with millimeter precision? The most common theory involves earthen ramps. Workers would build a massive ramp of soil and rubble against the growing wall, then drag the stones up this incline to the desired height. This seems logical, but the scale of such ramps is staggering. For a wall the size of Sacsayhuaman, the ramp would have been a monumental construction in itself, requiring the movement of more earth and stone than the fortress it was meant to build. And then, once the wall was complete, this enormous ramp would have to be completely dismantled and hauled away. Where is the evidence for that? We find no vast deposits of ramp material at these sites. The final positioning is the most delicate act of all. How do you nudge a multi-ton block the final few inches into its perfect interlocking seat? Levers and ropes made from natural fibers could provide some control, but the fine adjustments needed for the joints at Puma Punku or Ollantaytambo suggest a level of control that seems to defy simple physics. This leads to a haunting possibility. What if the true tool for transportation and lifting was not a physical device, but a forgotten knowledge of physics itself? Could these engineers have discovered principles of acoustic levitation or harmonic resonance that allowed them to neutralize the weight of stone, making it move almost effortlessly? While it sounds like science fiction, it is a theory that persists in local oral traditions, a whisper that the ancestors knew how to make the stones sing, and in their song they became light. The silence surrounding their methods is a profound statement. It suggests their greatest tools were not objects that could be left behind, but a system of knowledge so advanced and so specialized that when the cultures that nurtured it faded, the knowledge itself evaporated, leaving only the impossible weight of its achievements. This mathematical perfection carved in stone points to a fourth, more abstract vanished tool. The instruments of measurement and alignment have disappeared without a trace. How did these builders achieve such unwavering precision in their angles and celestial alignments, working across continents and centuries? The evidence is everywhere you look. At Machu Picchu, windows and doorways are framed with such exacting right angles they appear machined. The entire complex is oriented to the cardinal directions with a precision that would require sophisticated surveying. Structures from the Inca to the Tiwanaku employ repeating geometric ratios, a consistent system of proportions that creates a hidden harmony in their architecture. This was not guesswork, it was applied mathematics on a grand scale. Simple tools like knotted cords for measuring or wooden T-squares for checking angles could achieve basic layouts. But could they maintain a perfect straight line for kilometers, as seen in the Nazca geoglyphs, or ensure that a wall in Cusco and a temple in Bolivia were built using the same exact unit of measurement. The dimensional consistency across sites separated by hundreds of miles suggests standardized measurement systems and precision instruments we have yet to discover, as metrology expert Dr. Sarah Johnson notes. This implies a shared or inherited technological knowledge, a universal standard that guided different cultures. The astronomical alignments present an even greater challenge. At Chavín de Huántar, light shafts capture the solstice sun with pinpoint accuracy. At Sacsayhuamán, the zigzag walls mirror celestial patterns. To achieve this, the builders needed more than just observation. They required tools for accurately tracking the sun's path across the sky throughout the year, for plotting the movement of stars, and for translating those complex celestial coordinates into permanent stone alignments. What were these devices? Perhaps they used advanced versions of the simple gnomons or shadow casting sticks, or constructed intricate sighting pools that reflected the night sky. But the tools sophisticated enough to deliver the precision we see have not survived, or perhaps we simply do not recognize their remains. The most telling clue lies in the stone joints themselves. The perfect multi-angled fits of polygonal masonry require more than just skilled stone carving. They demand an initial layout of breathtaking geometric complexity. Each irregular block had to be conceived and measured in relation to its neighbors before a single blow was struck. This suggests the use of templates or sophisticated gauges, tools that could transfer unique, complex shapes from a master plan onto raw stone. Where are these templates? Made from wood or leather, they would have decayed long ago. The water level, a simple tool using water's natural tendency to find its own level, could explain how they achieved flat foundations on mountainous terrain. Yet even this basic device leaves no archaeological signature. The vanishing of these measuring tools is perhaps the most profound loss. It represents the disappearance of the very language, the system of thought, that made these wonders possible. We are left with the magnificent sentences of their architecture, but the grammar that structured them is gone. Legends whisper of a time when stone itself became obedient. This is the stone softening hypothesis, perhaps the most controversial and captivating explanation for the impossible stonework of the ancients. It suggests the builders possessed a profound secret, a way to temporarily alter the very physics of rock, making it as pliable as wet clay. The idea stems from persistent indigenous stories, some of which were recorded by early Spanish chroniclers. They wrote of certain plants whose saps or extracts, when applied to stone, could cause its surface to soften, allowing it to be molded and shaped before it hardened back to its original, diamond-like strength. The notion seems fantastical, yet it offers a seductive solution to the mystery of the seamless joints and flowing, molded appearances seen at sites like Sacsayhuamán. Could there be a scientific basis for these tales? Researchers have identified several native South American plants with highly acidic or caustic properties. One leading candidate is the sap from the Puya raymondii plant, a botanical giant of the high Andes. Another possibility lies in extracts from various jungle vines, known to local peoples for their ability to break down organic matter. In laboratory settings, scientists have tested these and other substances on samples of andesite and granite. Some have shown a limited ability to etch or dull the stone's surface, but the results fall dramatically short of the legendary effect. The substances do not make the rock malleable. They cannot explain how a 50-ton block could be perfectly shaped and fitted. As materials scientist Dr. Kenji Tanaka observes, while we cannot rule out some form of chemical assistance, no proposed method fully explains the precision and scale of the stonework we observe. Beyond plant chemistry, another branch of this theory explores the power of sound. local oral histories sometimes speak not of potions but of frequencies. The idea is that specific resonant vibrations, perhaps produced by large drums or chanting, could have been used to temporarily reduce the gravitational pull on a massive stone or to subtly rearrange its crystalline structure, making it easier to work. Modern experiments in acoustic levitation, where sound waves are used to suspend tiny objects in mid-air, show that the principle is scientifically valid, albeit on a microscopic scale. Scaling this effect up to manipulate 100-ton blocks would require an energy source and a technological understanding that seems to belong to the far future, not the ancient past. The geological evidence on the stones themselves is equally inconclusive. Some researchers point to the vitrified or glass-like appearance of certain surfaces, suggesting exposure to extreme heat that could have softened the rock. Yet this is not a consistent feature across all sites. If such a powerful technology existed, capable of reshaping mountains, where are the vats for brewing the chemical compounds? Where are the tools for applying them? The industrial scale required to build a site like Puma Punku using stone softening techniques would have left behind an immense and unmistakable archaeological footprint. Its complete absence is a silent but powerful argument against the theory. The stone softening hypothesis lies in a tantalizing space between myth and potential reality. It speaks to a deep human desire to solve the mystery with a single, elegant key, but the evidence remains stubbornly out of reach, forcing us to wonder if the true secret was even more sophisticated, a lost science that we have not yet begun to imagine. A more unsettling possibility is that these builders possessed a technology that was systematically erased. The lost high-technology hypothesis dares to suggest that pre-Columbian societies developed sophisticated tools and machines that have simply not survived the relentless passage of time. What if the precision we see is not a mystery of primitive methods, but the direct result of advanced engineering that has since vanished from the world? This theory forces us to ask what such technology might have actually looked like. Perhaps they utilized complex pulley systems and geared winches made of wood and fiber, devices capable of hoisting massive stones with an efficiency we have not credited them with. The consistent parallel cut marks on andesite blocks could be the direct signature of powered rotary saws. Imagine a machine not of steel, but of hardened copper alloys and stone components, driven by water power or the coordinated force of many people, its blade charged with a diamond-infused abrasive slurry. Such a device could explain the uncannily flat surfaces and repetitive, modular blocks found at sites like Puma Punku. The scarcity of evidence then becomes a question of materials. If their most advanced tools were constructed from perishable substances, the answer is clear. Intricate machines built primarily from hardwoods, intricate rope systems, and leather drive belts would decay into dust within centuries, leaving behind only the stone they were used to shape. How could such comprehensive technical knowledge be completely lost? History is filled with examples of technological regression. Historian of technology Dr. Michael Petrov reminds us that technological regression is not uncommon in history. The Bronze Age collapse saw the loss of many advanced techniques across multiple civilizations. A similar cataclysm could have befallen the engineers of South America. A devastating pandemic, a prolonged period of climatic chaos, or a brutal conquest could have shattered the social order, wiping out the specialized guilds of artisans and engineers who held this knowledge. The survivors, focused on mere subsistence, would have lacked the infrastructure and the need to maintain such complex tools, and within a few generations, the knowledge itself would fade into legend. Consider the Olmecs of Mesoamerica, whose colossal head sculptures demonstrate an early mastery of stone, yet whose societal collapse left their tools and techniques obscured. This theory does not require alien intervention, only a recognition that human ingenuity is capable of great leaps, and that those leaps can be tragically fragile. It challenges our linear timeline of progress, suggesting that the path of innovation is not a constant upward climb, but a story of peaks and valleys, with some peaks lost so completely in the mists of time that we mistake their achievements for miracles. Perhaps the true marvel lies not in what they had, but in what they did with it. A third explanation challenges the need for any vanished technology at all, suggesting that these impossible structures were created with nothing more than stone, wood, and fiber, wielded with a level of skill we can barely comprehend. This is the sophisticated primitive tools theory, where extraordinary results emerge from simple means perfected over generations. Experimental archaeologists have dedicated their careers to testing this very idea, attempting to replicate the ancient work using only the tools these cultures are known to have possessed. The results are humbling. They begin with stone-on-stone percussion. A worker holds a hard river cobble and strikes a precise point on a granite block, not with brute force, but with a controlled, repetitive tapping. With each impact, a small flake of stone pops off. It is a painstaking process, but over thousands of hours, a rough shape begins to emerge from the raw rock. The true finesse, however, comes next with abrasives. Teams use simple wooden saws and drills, but the cutting power comes from the slurry. By adding quartz sand or even harder abrasive grit to water, and dragging a wooden saw back and forth through the mixture, they can slowly, methodically, slice through even the toughest andesite. The sand particles, harder than the rock itself, become millions of microscopic cutting teeth. This explains the straight cuts and the parallel striations. The drill holes with their perfect spiral grooves are recreated using a hollow reed or wooden tube, spun with a bow drill and fed with the same abrasive slurry. The process is unimaginably slow, but it works. The final, gleaming polish is achieved by rubbing the stone for days or weeks with progressively finer abrasives, until the surface shines like a mirror. This was not a quick endeavor. It was the life's work of master artisans. Experimental archaeologist Dr. Lisa Montgomery observes that we consistently underestimate what can be achieved with simple tools in the hands of highly skilled craftspeople working within sophisticated organizational systems. This points to the most crucial tool of all, one that has indeed vanished, the tool of perfected knowledge. Imagine a guild of stonemasons where techniques were refined and passed from parent to child over centuries. Each generation would add its own small innovation, its own deeper understanding of the stone's grain and fracture points. This cumulative wisdom, this living library of tactile experience, is a form of technology that leaves no physical trace. The organizational system was the engine that made it possible, coordinating thousands of workers to quarry, transport, and fit these stones was a logistical masterpiece. It required a society capable of planning projects that would outlive every individual who started them. The true tool was a shared vision and a social structure that could marshal human energy with breathtaking efficiency. So, could the answer be less about mysterious technology and more about the sheer power of sustained human ingenuity? This perspective forces us to see these sites not as puzzles left by a superior, lost science, but as monuments to what human hands, minds, and unwavering patience can accomplish. The real mystery then shifts from the tools they used to the society that could inspire such a profound and enduring commitment. The real machinery behind these stone marvels was not made of metal or stone, but of human collaboration. We must visualize an organizational network so vast and efficient that it could quarry a mountain in one location, transport its heart across a river and up a valley, and position it with perfect accuracy, all without a single written blueprint or instruction manual. This was the ultimate management challenge. Anthropologist Dr. Gabriela Silva observes that the organizational achievement is as impressive as the engineering. Moving stones required moving people, food, and resources on an enormous scale. The evidence for this is etched into the landscape itself. Archaeologists find the remains of temporary worker settlements, storage complexes for tools and food, and extensive road systems that connected quarries to construction sites. These are the bones of a massive, living enterprise. Consider the labor estimates for a site like Sacsayhuaman. Scholars calculate that just the quarrying, transport, and initial shaping of its largest stones would have required crews of several thousand people working in coordinated shifts. This was not a chaotic mob. It was a society operating with a sophisticated division of labor. There would have been specialized teams of quarrymen, road builders, rope makers, surveyors, and the master masons who executed the final, precise fitting. Each team depended on the other, creating a seamless production chain. How did they schedule such an immense undertaking? The agricultural calendar held the key. Major construction would have been planned for the dry season, when farmers were free from their fields and the weather permitted the movement of heavy loads across the land. This cyclical rhythm meant that a project was not just a construction site, but a seasonal, society-wide event. The most profound mystery lies in knowledge transmission. How do you teach the precise geometry for fitting a polygonal block, or the exact angle for a celestial alignment without writing it down? The answer was a system of apprenticeship and oral tradition. Master builders would train their children and selected students through hands-on demonstration, using songs, stories, and rhythmic chants to encode complex mathematical and engineering principles. This living library of knowledge was passed from one generation to the next, ensuring that a project started by a great-grandfather could be completed by his great-grandson with no loss of fidelity or vision. What force could possibly motivate such sustained, monumental effort over centuries? The answer lies in a world where politics and spirituality were inseparable. Building these structures was not just a civic duty, it was a sacred act. The ruler or priest class provided the central vision, organizing labor through a system of reciprocal obligation known as mitta. Workers contributed their time as a form of tax or community service, and in return, they received food, drink, and the profound social prestige of participating in a project that connected them to the gods and the cosmos itself. The construction site became a physical manifestation of a social contract, a place where the entire society reaffirmed its identity and its place in the universe. The true vanished tool, then, may have been this invisible framework of shared belief, a meticulous organization, and intergenerational dedication. We are left to wonder if our modern world, with all its digital planners and management software, could ever muster the collective will to build something meant to last for 1,000 years. The flawless repetition of architectural styles across centuries hints at a powerful system of knowledge transmission, one that operated entirely without written words. How do you teach the precise geometry for fitting an irregular stone, or the exact celestial alignment for a temple when there is no instruction manual to consult? The answer lies in a living library of skill, passed directly from master to apprentice through generations of dedicated artisans. Within families or specialized guilds, complex engineering principles were not written down but woven into the very fabric of daily life. A father would teach his son not with diagrams but by guiding his hands, showing him the exact angle to hold a stone hammer, the specific sound a rock makes when it is ready to fracture, and the subtle feel of a perfectly flat surface. This was knowledge encoded in muscle memory and sensory experience, a cumulative wisdom refined over lifetimes. These artisan families were the guardians of a priceless intellectual heritage. their very identities tied to the specific skills needed to shape the world. The evidence for this standardized, long-term training is visible in the stones themselves. The same precise angles, the same interlocking joints, and the same unit of measurement appear in sites built hundreds of years and miles apart. This consistency across vast distances and time suggests a shared or inherited curriculum, a universal language of construction taught in a similar way from one generation of builders to the next. Beyond hands-on apprenticeship, these cultures likely employed sophisticated mnemonic devices. Complex technical sequences could have been encoded into songs, rhythmic chants, or ceremonial dances, turning abstract mathematical formulas into memorable, repeatable patterns. There is also the intriguing possibility that the quipu, the complex system of knotted strings used by the Inca for accounting and census data, held a deeper purpose. Knowledge systems expert Dr. Alejandro Mendoza suggests that the loss of engineering knowledge following the Spanish conquest was catastrophic. He notes that we may be looking at only fragments of what these cultures understood. It is conceivable that certain quipu patterns served as memory aids for architectural plans or engineering formulas, with the knots representing specific measurements, ratios, or construction sequences. This intricate web of oral tradition and hands-on training was incredibly resilient for centuries, but it possessed a critical vulnerability. The knowledge lived only in the minds and hands of the people. When European contact triggered a demographic catastrophe through disease and warfare, it shattered this delicate chain. The specialized artisan families were decimated, their apprentices lost before they could learn the deepest secrets. The new colonial rulers had little interest in preserving native engineering techniques, actively suppressing indigenous languages and traditions. The songs were no longer sung, the hands that held the stones grew still, and the living library of knowledge, built over 1,000 years, was effectively burned in a single, brutal century. The true vanished tool, therefore, was not just a physical object, but this entire ecosystem of intergenerational learning. Its disappearance forces us to ask a profound question about our own world. In an age of digital storage and instant access, what priceless knowledge might we be losing simply because we have forgotten how to pass it on through our hands and our voices? This global perspective reveals a fascinating pattern of human ingenuity. When we place South American stonework beside the pyramids of Egypt or the ziggurats of Mesopotamia, we see a common drive to build monuments that touch the heavens, yet the methods employed could not be more different. The Egyptians, for instance, used copper chisels and stone pounders on relatively soft limestone, leaving behind vast quarries littered with these very tools, along with wooden mallets and sledges. We can trace their technological footprint in the archaeological record. Similarly, in China, the advanced bronze casting used for intricate ceremonial vessels is well documented. The difference lies not in ambition, but in the materials and the resulting evidence. Comparative archaeologist Dr. Hannah Weiss observes that the South American achievement is unique in its combination of massive scale and microscopic precision. We do not see this exact combination elsewhere in the ancient world. The Egyptians achieved breathtaking scale with the pyramids, but the precision of their stone fitting, while impressive, does not match the complex, interlocking joints of Inca masonry. The Romans were masters of precision with their concrete and arches, but their work often involved smaller, more uniform blocks. South America presents a paradox where the largest stones are fitted with the smallest tolerances. This distinct focus helps explain the mystery of their tools. Cultures that worked primarily with softer stones or used metal for ornamentation left behind a clear trail of their implements. The South American engineers, however, were tackling granite and andesite, materials so hard they would have rapidly destroyed the copper tools we commonly find elsewhere. If their primary tools were made of equally perishable materials like wood, fiber, and specialized abrasives, it is little wonder they vanished, leaving only their magnificent stone accomplishments behind. The contrast in metal tool development is particularly telling. In Mesopotamia and Egypt, metalworking evolved to produce not just jewelry, but also functional tools for construction and warfare. We have found their saws, axes, and chisels. In South America, metallurgy took a different path, focusing on artistic and symbolic objects in gold and silver, with utilitarian tools largely remaining in the realm of stone and bronze. This cultural choice meant their most advanced metal alloys were not applied to the problem of hard stone construction, pushing them to develop alternative and now invisible techniques. Even in the Americas, a revealing comparison exists with the Maya. The Maya carved intricate facades and lintels from limestone using stone tools, and we find abundant evidence of their chert chisels and hammerstones in workshops. Their stone was softer and their tool-making debris survives. The South American case, working harder rock, seems to have required a different, more ephemeral toolkit. This extends to the challenge of transportation. The Egyptians moved colossal obelisks on giant sledges across lubricated paths, a method depicted in their own art. The South American methods, while perhaps using similar principles of sledges and ramps, were applied on a terrain of impossible steepness and altitude, a context so unique it may have demanded unique solutions that left no durable remains. So, what does this global comparison ultimately tell us? It suggests that the uniqueness of South American engineering, its specific combination of hard stone, mountainous terrain, and a cultural focus on perfect seams, created a technological niche. Their solutions were so specialized, so perfectly adapted to their environment and goals, that when their civilization faded, the knowledge dissolved because it was not written down but lived in the hands of the artisans, and their tools were not of metal but of perishable substances and perfected skill. This global view does not diminish their achievements but rather highlights a profound truth about technology. It is not a single, linear path, but a branching tree of solutions, and some of the most brilliant branches can, under the right conditions, vanish without a trace. The very stones these builders chose present their own formidable puzzle. Across the Andes, the primary construction materials were not just rocks, they were geological challenges of the highest order. At Puma Punku, the stone is andesite, a volcanic rock born from the heart of the earth, renowned for its extreme hardness and dense, interlocking crystalline structure. To even scratch its surface with another stone requires immense, focused force. Yet at this site, we see andesite blocks carved with what appear to be machined edges and perfect 90-degree angles. Then at Ollantaytambo, the challenge shifts to pink granite, another igneous giant, prized for its durability but notoriously difficult to shape due to its coarse, granular composition that can fracture unpredictably. Working granite demands not just power, but an intimate knowledge of its internal grain. These were not the soft limestones or sandstones used by other ancient cultures, which are far more forgiving to stone and bronze tools. The South American engineers consistently sought out the most difficult materials available and then mastered them. Geologist Dr. Robert Chen observes that the ancient engineers displayed a sophisticated understanding of material properties. They selected and worked each stone type according to its specific characteristics. This is evident in the varied techniques visible at different sites. On the granite of Sacsayhuaman, we see the characteristic rounded, pillow-like facets of precise percussion work. On the andesite of Puma Punku, we find those unnervingly straight cuts and flat surfaces that suggest a different, perhaps abrasive-based method. This indicates a versatile and adaptable technological approach, not a single, rigid formula. They understood that andesite, being harder and more homogeneous, could be worked into sharp, precise geometries, while granite, with its tougher, granular structure, was better suited to the massive, interlocking polygonal style that could absorb seismic shocks. Modern geological sourcing studies add another layer to this mystery. Using X-ray fluorescence and other techniques, scientists can trace a cut stone back to its exact quarry. These studies reveal that these builders were not just using the most convenient local rock. They often went to extraordinary lengths to procure specific stone types from quarries many kilometers away. This was not random selection. It was a deliberate choice based on a deep, accumulated knowledge of material science. They knew which stone had the best compressive strength for a foundation, which would polish to a brilliant sheen for a temple wall, and which possessed the right acoustic properties for a ceremonial space. The consistent, high-quality work across these different, challenging stone types tells us something profound about their tool kit. It had to be versatile enough to handle granite, andesite, and limestone with equal finesse. A simple stone hammer might work on one type of rock but would be useless on another. This suggests their true technology was a system, a combination of different tools and techniques, and perhaps most importantly, the ingrained knowledge of when and how to apply each one. The geology itself becomes a silent witness to their genius, proving that their greatest tool may have been an unparalleled understanding of the very earth they built upon. The ground beneath these ancient sites holds the only physical evidence of the tools themselves. At major construction zones like Ollantaytambo and the quarries of Rumacolca, archaeologists have unearthed thousands of artifacts, a tangible yet perplexing toolkit. The most common discoveries are hammerstones, simple river cobbles of hard quartzite or granite, worn smooth from repeated impact. Alongside these are found bronze crowbars and chisels, though these metal implements are surprisingly few and often appear too soft for the monumental tasks at hand. At a site like Puma Punku, excavations have revealed smaller, more specialized tools, including stone abrasives and simple copper reamers that might have been used for finer work. These finds are real, they are numerous, and they are displayed in museums, yet they present a profound contradiction. As archaeologist Dr. Patricia Lopez notes, we have found thousands of stone tools at these sites, but they do not fully explain the precision we see in the finished architecture. The discovered tools seem suited for the rough, initial work of quarrying and shaping, but not for the final, almost surgical precision of the fitting and polishing. This gap between the tools we have and the work we see is the very heart of the mystery. To bridge this divide, researchers have turned to the stones themselves, reading the subtle marks left by the builders as a unique historical document. The tool marks tell a complex story. On some granite surfaces, you can see the characteristic pitting and stippling from percussive strikes with hammerstones. On the andesite at Puma Punku, however, the evidence shifts to long, straight grooves and parallel striations, marks that suggest the persistent back and forth motion of a sawing tool, not a pounding one. There are also the telltale spiral grooves inside drill holes, indicating a rotary motion. None of these marks, however, show the distinctive gouges of a metal chisel. This absence is deafening. It implies that the final finishing was achieved with techniques that left no recognizable metal signature, perhaps relying entirely on abrasives or other methods we have yet to identify. Experimental archaeology has been crucial in testing these ideas. Teams of researchers have taken the very tools found at the sites, bronze chisels and stone hammers, and attempted to replicate the ancient work. They can indeed quarry a block and rough out a shape, but the process is brutally slow and the results lack the flawless seams and mirror finishes. When they use wooden saws with sand and water as an abrasive, they can eventually cut through andesite, leaving similar striations. Yet the scale and perfection remain out of reach. Their cuts are slower, less straight, and cannot account for the incredible complexity of the H-blocks. These experiments prove that the basic tools could accomplish the basic tasks, but they also highlight a massive gap in efficiency and precision. The tools work, but they do not work that well, at least not in the hands of modern experimenters over limited timeframes. This points directly to the problem of perishable materials. The archaeological record is brutally biased against organic substances. Imagine the true toolkit of these engineers. It would have included intricate wooden frames for guiding saws, complex rope systems for leverage and transport, leather straps and drive belts for any potential machinery, and containers for holding specialized abrasive slurries. All of these items, made of wood, fiber, and hide, would have decayed into dust within centuries in the South American climate, leaving no trace for us to find. The most sophisticated components of their technology, the jigs, the templates, the measuring devices, were likely made from these very materials. What we have discovered are the durable stone and metal remnants of the toolkit, the equivalent of finding a modern construction worker's hammer but missing the entire crane, the laser level, and the blueprint. So what does the existing evidence actually tell us? It confirms that these cultures possessed a robust and practical technology for moving and shaping stone. But it also reveals a staggering gap. The evidence on the ground cannot account for the final leap to perfection. The real tools, the ones that achieved the impossible precision, were either so specialized they were collected and curated out of existence, or they were made of knowledge and materials that have simply vanished from the earth, leaving us with the durable bones of their work and the haunting ghost of their methods. The smooth, curved surfaces of these ancient stones hold secrets invisible to human eyes. Modern science is now giving us the vision to read them. Through advanced 3D scanning and material analysis, researchers are uncovering a hidden world of engineering precision that earlier generations could only guess at. Teams have deployed laser scanners across sites like Machu Picchu and Ollantaytambo, creating digital models of such high resolution that they can measure the flatness of a stone surface to within a fraction of a millimeter. What these scans reveal is a consistency that borders on the mechanical. The angles are not merely close to 90 degrees, they are perfect. The joints between stones, when analyzed digitally, show a complex topography of subtle concavities and convexities that interlock with their neighbors in a way that simple hand fitting could not achieve. This is not rough construction, it is a technology of microengineering. As materials analysis expert Dr. Jennifer Wright observes, modern technology allows us to see details invisible to the naked eye. We are discovering subtleties in the workmanship that earlier researchers missed. These scans provide the first hard data on the true scale of the achievement, offering a digital blueprint of the builder's intent. On a microscopic level, the story becomes even more fascinating. Researchers use portable digital microscopes to examine tool marks at 100 times magnification. On a granite block from Sacsayhuaman, they might see the faint, repetitive stippling from a stone hammer, but on an andesite block from Puma Punku, the story changes. Under the lens, the surface reveals long, parallel striations, grooves so consistent in their spacing and depth that they suggest the use of a rigid, guided sawing tool, not freehand chiseling. The microscopic world also reveals the secrets of the polish. On some stones, scientists have identified a thin, vitrified layer, a kind of glass-like coating that could only be achieved through intense, localized friction or heat, a finishing technique far beyond simple sanding. This non-destructive testing is crucial, allowing scientists to gather immense amounts of data without so much as touching the ancient stones, preserving these sacred sites for future generations while unlocking their past. Perhaps the most powerful new tool is computer simulation. Engineers can now create virtual models of a multi-ton block and test different theories of transportation and placement. They can simulate the effects of log rollers on a steep slope, calculating the precise number of workers and the amount of force needed to prevent a catastrophic runaway. They can model the construction of an earthen ramp for Sacsayhuamán, calculating the volume of material and the time required for its building and subsequent removal. These simulations often reveal the staggering practical difficulties that simpler theories overlook, forcing a reconsideration of the methods. A simulation might show that dragging a 50-ton block up a steep incline with just ropes and manpower would require an impossible number of people, suggesting that some form of mechanical advantage, like a forgotten type of winch or lever system, must have been employed. Each scan, each microscopic image, and each simulation adds another piece to the puzzle. They do not always provide easy answers, but they strip away speculation and replace it with data. They confirm that the precision we instinctively feel is real, measurable, and utterly baffling. The hope is that as these technologies advance, as scanning resolution increases and artificial intelligence helps analyze the vast datasets, we may finally see the ghostly outline of the lost tools themselves, not in stone, but in the perfect digital shadows they left behind. These magnificent stone structures were not merely buildings, they were conversations with the cosmos. To understand the tools of these engineers, we must first understand the world they were trying to build, a world where the physical and spiritual realms were seamlessly intertwined. The act of construction was a sacred ritual, a way of anchoring celestial order onto the chaotic earth. Every stone laid was a prayer, every wall a reflection of a mountain, and every temple a gateway to the divine. The perfect seams in their masonry were not just a technical goal, they were a spiritual necessity, creating a sacred space so seamless it could contain the presence of a god. Anthropologist Dr. Carlos Mendez observes that we cannot separate the technical achievement from its cultural meaning. The buildings expressed cosmological ideas as much as engineering principles. This worldview fundamentally shaped their technological choices. Why use such impossibly hard stones like andesite and granite? Because these were the bones of the earth, the most permanent and powerful materials, worthy of housing the divine and ensuring a structure's survival for eternity. The same cultural value that prized permanence and sacred precision would have discouraged the use of tools that were ephemeral or left crude, ugly marks. The tools themselves, therefore, had to be as refined and respectful as the finished product. This might explain why we find no rough, utilitarian metal chisels in great numbers, their use perhaps reserved for rougher, unseen work, while the final, sacred fitting was accomplished with methods that were themselves considered ritually pure, perhaps even involving chants, plant-based compounds, or acoustic techniques that were part of a ceremonial process. The entire landscape was their blueprint. A river's flow, a mountain's silhouette, the path of the sun. These were not just features to work around, they were active participants in the design. The zigzag walls of Sacsayhuamán mirrored the lightning of the sky god Ilapa. The alignment of a temple doorway with the solstice sunrise was not an advanced feature, it was the entire point. Engineering knowledge was not a separate discipline, but a thread woven into a larger tapestry of knowledge that included astronomy, agriculture, and mythology. The same understanding of hydraulics that prevented flooding at Chavín de Huántar also created the roaring water sounds that defined its religious ceremonies. The master stonemason was also an astronomer, a priest, and a philosopher. His toolkit was as much about understanding the stars and the spirit of the rock as it was about physical implements. This cultural dimension offers a profound clue to the mystery of the vanished tools. If the most advanced techniques were sacred knowledge, closely guarded by specific lineages of artisans and embedded in ritual, then their disappearance becomes more understandable. When those lineages were broken by conquest and disease, the deeply contextual knowledge, the songs, the recipes, the precise movements required to make the stone obey, would have been the first things to vanish. The tools were not just objects, they were extensions of a worldview. And when that worldview was shattered, the most sophisticated tools of all, the ones made of knowledge and belief, simply evaporated, leaving behind only the eternal stones that were their ultimate expression. The relentless environment of South America has been a silent, decisive force in this mystery. While the stones endure, the tools used to shape them have faced a constant war of attrition against humidity, temperature, and chemistry. Preservation specialist Dr. Amanda Torres explains that the environmental conditions across much of South America are particularly challenging for preserving metal and organic materials. This creates significant gaps in our understanding. In the bone-dry deserts of the coast where the Nazca laid their lines, organic materials can last for centuries. But in the high Andes, the situation is completely different. The cycle of freezing nights and sunny days, the torrential seasonal rains, and the highly acidic soils create a perfect storm for decay. A wooden tool left exposed would warp, crack, and be consumed by fungi and bacteria within a few decades. A bronze chisel buried in damp, acidic soil would slowly transform into a fragile green crust, its original shape and strength lost to corrosion. Even stone hammers, the most durable items, can be broken down by repeated freezing and thawing, their working edges crumbling away to anonymous cobbles. This is not a minor detail, it is a fundamental bias in the archaeological record. The evidence we find is not a complete inventory of what existed, it is only what was tough enough or lucky enough to survive. Compare this to the arid, stable tombs of Egypt, where we find intact wooden sledges, leather ropes, and even woven baskets alongside the pyramids. Or consider the waterlogged, oxygen-free mud of European bogs, which have preserved wooden carts and tools for thousands of years. South America's most dramatic engineering sites lack these perfect preservation environments. The constant seismic activity adds another layer of destruction. Earthquakes have not only toppled walls but have also triggered landslides and floods, burying entire workshops under meters of debris or scouring them clean from the landscape. A storage hut filled with specialized wooden frames and fiber ropes could have been pulverized and washed down a mountainside in a single cataclysmic event, leaving no trace for future archaeologists to find. Furthermore, the environment itself has changed over the millennia. A quarry site that was arid when the Chavín were working may have later become a swampy basin, submerging and rotting any remaining tools. A valley used for tool production could have been buried under volcanic ash, preserving everything perfectly, only to have that same layer eroded away centuries later, taking the evidence with it. This environmental perspective forces a humbling realization. How much of the tool mystery is not a mystery of advanced technology, but simply one of poor preservation? The answer could be a great deal. The sophisticated primitive tools theory gains immense weight when you consider that the most intricate components of their toolkit were likely made of wood, leather, and plant fibers, materials destined to return to the earth. This does not mean the tools were simple, but that they were perfectly adapted to their task and tragically ephemeral in their composition. It reframes the entire search. Future discoveries may not come from a dramatic find of a strange machine. but from the careful analysis of a soil impression, the ghost of a rotted wooden handle preserved in corrosion on a bronze fragment, or the microscopic residue of a specific plant-based abrasive clinging to the bottom of a stone vessel. The environment has hidden the tools, but it may also hold the key to finding them. The whispers of the past still speak through the voices of the living. Across the Andes, contemporary Quechua and Aymara communities maintain a profound, unbroken connection to these ancient sites, not as ruins of a dead people, but as active parts of their cultural and spiritual landscape. Their oral traditions and legends offer a fundamentally different kind of evidence, one written not in stone or soil, but in memory and story. These narratives often describe the construction process in ways that challenge our material-based logic. Some stories speak of the stones being softened, not with tools, but with the sap of specific, sacred plants, a knowledge given by the mountain spirits themselves. Other legends tell of a time when the very laws of physics were different, when the great stones could be moved by sound, by the blast of a trumpet or the focused will of a shaman, making them light enough to be carried through the air. For these communities, the question is not how they moved 50-ton blocks, but why they would need to when the ancestors possessed the spiritual authority to command the stone's obedience. This perspective reframes the entire mystery. The precision and scale of the work are not attributed to complex machinery, but to a harmonious relationship with the natural world, where human intention, ritual, and the spirit within the rock collaborated to create something eternal. Cultural historian Dr. Elena Quispe observes that oral traditions often preserve technological knowledge in metaphorical form. The challenge is learning to interpret these metaphors correctly. A story about a plant that softens stone might not be a literal recipe, but a metaphorical key to understanding a sophisticated chemical process involving plant-based acids used in the final polishing stages. A legend of stones moving to the sound of a trumpet could be a cultural memory of a highly coordinated workforce using rhythmic chants and acoustic signals to move in perfect unison, creating a synchrony that made the immense task seem almost effortless. The preservation of this knowledge over centuries, even in the face of conquest and cultural suppression, is a testament to its resilience. It has been kept alive in the songs sung during festivals, in the stories told by elders to children, and in the rituals still performed at these sacred locations. This living knowledge system forces a critical ethical question. For too long, archaeological interpretations have proceeded without meaningful collaboration with the descendant communities who hold the keys to this cultural context. The ethical dimension of this research is clear. It requires a respectful partnership where indigenous knowledge is not merely mined for data, but treated as a valid and essential framework for understanding. When a community elder points to a specific rock formation and recounts a centuries-old story about its placement, that is not a myth to be dismissed. It is a piece of evidence, a clue embedded in a living culture. What insights can this collaboration provide? It might guide archaeologists to look for evidence of specific plants in soil samples near quarries. It could help interpret strange architectural features not as practical handles, but as sacred symbols related to these construction legends. By bridging the gap between the material evidence of archaeology and the living memory of oral tradition, we might finally begin to see the complete picture. The vanished tools may not have been just physical objects, but a deeply integrated system of spiritual belief, botanical knowledge, and social organization. A technology of the mind and spirit that left its most durable signature not in the tools themselves, but in the timeless stones they were used to create. These staggering stone cities required an economy of equal ambition. Behind every perfectly fitted block stood a hidden network of resource extraction, specialized labor, and long-distance trade that formed the true engine of these projects. The scale of construction at a place like Sacsayhuaman or Puma Punku reveals a society with significant economic surplus. This was not a hand-to-mouth civilization. It was one capable of producing enough food and goods to support thousands of people who were not farming, but were instead dedicated full-time to the arts of engineering. Economic archaeologist Dr. Benjamin Lee observes that the economic achievement behind these constructions is monumental. They required surplus production, specialized labor, and complex distribution systems. This surplus was the fundamental fuel. Without vast stores of potatoes, quinoa, and dried meat from state-managed warehouses, the workforce would have starved. Without the textile workshops producing immense quantities of rope and slings from llama and alpaca wool, the stones could never have been moved. The economy itself was the most vital tool, one that has left traces not in stone, but in the remains of storehouses and the patterns of ancient roads. We find evidence of specialized craft production centers away from the main construction sites. Archaeologists uncover areas dedicated solely to making stone tools, or precincts for weaving the incredibly strong cables needed for transport. This division of labor was crucial. Just as a master mason focused on the final fitting of a stone, another artisan spent a lifetime perfecting the manufacture of the bronze crowbars used in the quarry. This specialization hints at a sophisticated economic system where knowledge and resources were efficiently channeled toward a single, monumental goal. The logistics of feeding and housing these workforces was a colossal undertaking in itself. Temporary worker settlements sprang up near major projects, complete with their own kitchens, water supplies, and administrative centers. The provisioning of these camps required a distribution network that stretched across the empire, with food and supplies flowing along well-maintained roads from state-owned farms and storage complexes. This was a command economy operating at its peak, capable of moving not just stone but sustenance on a breathtaking scale. What were the economic motivations for such an immense investment? The projects were not merely practical. They were powerful political and religious statements that reinforced the authority of the ruling class. By demonstrating the ability to reshape the very earth, a ruler showcased his control over both human and natural resources. Building a temple that aligned with the solstice sun was an act that cemented a spiritual contract with the gods, ensuring agricultural fertility and cosmic order for the entire society. The economic surplus was thus invested back into the system as a form of social and spiritual insurance. This economic context directly influenced tool development and use. Why invest generations in perfecting a complex, abrasive-based cutting system instead of developing harder metal alloys? The answer may lie in resource availability and economic strategy. South America had abundant, high-quality abrasive sands and stones, but sources of tin necessary for creating harder bronze were more limited and required control of long, vulnerable trade routes. It was economically more efficient to master the technology they could reliably source than to depend on a scarce imported resource. The economic foundation tells us that technologies were adopted or abandoned based on a complex calculation of cost, available materials, and social benefit. The choice to use massive polygonal masonry, for instance, was not just an engineering one. It was an economic declaration of permanence and power, a statement that this society had the wealth and will to build for eternity. Understanding this economic machinery provides another crucial piece of the puzzle, revealing that the vanished tools were supported by a vanished economy, a system of such intricate organization that its collapse would have made the reconstruction of such wonders economically impossible for those who came after. The search for answers is shifting from the stones themselves to the microscopic world they contain. Future discoveries may not come from a dramatic new find, but from the invisible residue clinging to ancient tools or hidden within the soil of a long-abandoned workshop. Archaeologists are now employing techniques like residue analysis, using advanced chemistry to identify microscopic traces of plants, minerals, or other materials on the surfaces of the few bronze and stone tools we have recovered. Finding the chemical signature of a specific plant sap on a stone polisher, for instance, could transform a legendary tale of stone softening into a tangible, scientific fact. Similarly, soil sampling at quarry sites is becoming increasingly sophisticated. By analyzing soil chemistry in areas where stones were worked, researchers can detect anomalous concentrations of elements that might point to the use of specific chemical compounds or abrasive slurries, creating a chemical map of the manufacturing process that has been invisible until now. Research Director Dr. Maria Santos observes that we are at an exciting moment where new technologies are allowing us to ask questions we could not ask before. The next decade may bring significant breakthroughs. This includes the use of isotopic analysis on metal artifacts. By studying the unique isotopic fingerprints of copper and tin in bronze tools, scientists can trace the metal back to its original mine, revealing vast, previously unknown trade networks that supplied these massive construction projects. This economic understanding is crucial, as it helps us comprehend the sheer scale of the organization required and may lead us to specialized tool production centers located far from the main building sites. Several promising locations are poised for renewed investigation. The quarry at Rumacolca, the primary source of the elegant limestone used in Cusco's finest structures, is still largely unexcavated. It holds the potential to reveal not just how stones were extracted, but the entire life cycle of a tool, from its manufacture to its eventual discard. In the surrounding soil, archaeologists hope to find the decomposed remains of wooden levers, fiber ropes, and the organic containers that held the all-important abrasives. Another site generating excitement is the sprawling pre-Inca complex of Tiwanaku itself, the city that built Puma Punku. Large areas remain buried, and a systematic, modern excavation could uncover the workshops and tool storage facilities that have eluded us for centuries. The key is to look beyond the monumental architecture and focus on the peripheral areas, the spaces dedicated to the gritty, practical work that made the magic happen. Even sites we think we know, like Ollantaytambo, are being re-examined with fresh eyes and new technology. Ground-penetrating radar surveys are being used to map subterranean features without ever breaking ground, searching for the foundations of the massive earthen ramps used for construction or the buried remains of worker camps that could contain a wealth of lost artifacts. The future of this research depends as much on preservation as it does on discovery. Every site that is damaged by erosion, uncontrolled tourism, or looting represents a permanent loss of data, a page torn from a book we are still learning to read. The meticulous conservation of these locations is not merely about protecting beautiful ruins, it is about safeguarding a priceless scientific archive. As our analytical techniques grow more powerful, the information we can extract from a single, undisturbed soil layer or a carefully documented tool fragment increases exponentially. A tiny sample taken today and properly stored could be analyzed in 20 years with technology that does not yet exist, potentially revealing secrets we cannot even conceive of now. The most thrilling prospect is the potential for an unexpected discovery. A sealed cave, a perfectly preserved context buried by a sudden landslide, or a collection of artifacts from a newly discovered, waterlogged site could provide the Rosetta Stone for this entire mystery. The collaboration between archaeologists, materials scientists, geologists, and indigenous knowledge keepers is creating a new, holistic approach to these ancient questions. We are no longer just studying stones, we are piecing together a lost world of innovation. And with each new technological lens we apply, the ghostly outline of the ancient engineer's true toolkit comes slowly, tantalizingly into focus. These vanished techniques challenge our modern assumptions about progress. In a world dominated by steel and silicon, the achievements of these ancient engineers stand as a powerful testament to alternative forms of brilliance. Their work matters now more than ever, not as a forgotten relic, but as a source of profound lessons for our own future. The precision of their stonework, built to endure for millennia, offers a masterclass in long-term durability. Our contemporary construction often prioritizes speed and cost, creating structures with a lifespan of decades. Their monuments, however, were built for eternity, with an understanding of materials and seismic forces that we are only now relearning through advanced computer modeling. Their entire operational model was powered by human ingenuity and renewable resources, not fossil fuels. They moved mountains without a single drop of petroleum, using the organized power of their society as their primary engine. This presents a compelling vision of large-scale innovation that existed in a sustainable balance with the environment, a paradigm we desperately need to rediscover. Technology historian Dr. James Wilson observes that these ancient achievements remind us that technological sophistication takes many forms. There are multiple paths to solving engineering challenges. This is not merely an academic point. By studying their diverse approaches, we expand our own problem-solving toolkit. Their use of specific stone types for different structural or ceremonial purposes reveals a deep materials science that could inspire new, sustainable composites. Their hydraulic systems at Chavín, which managed water through gravity and clever design rather than pumps, offer insights for modern storm water management and passive irrigation. The very mystery of their methods pushes the boundaries of what we believe is possible, forcing us to question if our current technological path is the only one. Preserving these sites is therefore not just about cultural heritage, it is about safeguarding a vast library of human ingenuity. These stones are pages in a global textbook of engineering, written in a language we are still learning to decipher. The collaborative systems that built them, the knowledge passed through generations without writing, and the seamless integration of science and spirituality all represent different ways of knowing and building. What can we learn from these mysterious engineers that remains relevant today? Perhaps the most vital lesson is that true innovation is not just about the tools you create, but about the enduring legacy you leave behind and the harmonious relationship you forge with the world you are shaping. Their silent, steadfast ruins ask us whether our own technological advancements will stand the test of time, or if they too will vanish, leaving behind questions for future generations to ponder. These stone enigmas ultimately ask us to reconsider the very nature of progress itself. We are left not with tidy answers, but with a profound and humbling realization. The greatest mystery may not be the specific tools that have vanished, but the entire mindset that conceived such perfection. Our modern world, built on digital precision and disposable materials, struggles to comprehend an engineering philosophy where the primary goal was not speed, but eternity. These structures were not designed for a human lifespan, but for geological time. This perspective alone forces a radical shift in how we measure technological advancement. As archaeologist Dr. Elena Rodriguez observes, the greatest mystery is not how they built these structures, but why we have been unable to fully understand their methods despite centuries of study. We have searched for missing machines when perhaps we should have been searching for a missing philosophy. The ancient engineers of the Andes saw no separation between the technical and the spiritual, between the act of building and the act of prayer. Their greatest tool may have been a unified vision of the world, one that we, in our fragmented disciplines, have lost the ability to see. The precision of their cuts, the endurance of their walls, and the celestial alignment of their temples all point to a different path of innovation, one rooted in deep observation, generational patience, and a sacred relationship with the materials of the earth. The search for their methods continues not as a pursuit of a lost gadget, but as a journey to reclaim a different way of thinking. Each new generation brings fresh eyes and new technologies to these ancient stones, hoping to glimpse a fragment of that lost wisdom. Perhaps the true legacy of these master builders is not the silent cities they left behind, but the enduring questions they force us to ask about our own place in time and about what truly lasts. These ancient stones leave us not with solutions but with a deeper sense of wonder. Your own perspective is a vital part of this ongoing investigation, so we invite you to continue the journey with us. Our channel is your portal to deeper explorations, from detailed breakdowns of specific sites like Puma Punku to reports on the latest archaeological finds that are slowly rewriting history. I am genuinely curious to hear your thoughts in the comments below. Which explanation for the vanished tools resonates most with you? Do you lean towards the idea of sophisticated primitive methods, or does the possibility of a lost high technology capture your imagination? Tell us which facet of this puzzle intrigues you the most. If you have been fortunate enough to walk among these ruins yourself, we would love to hear your personal stories and observations from the ground. To make sure you do not miss our upcoming investigations into other historical mysteries from across the globe, please subscribe to the channel and tap the notification bell. The narrative of South America's master builders is far from complete. Each passing year brings new scans, new excavations, and new interpretations that challenge what we thought we knew. Your engagement, your questions, and your shared curiosity are what fuel this search and keep these ancient stories vibrant and alive. The greatest lesson these engineers teach us might be this: the most profound journeys of discovery do not always start with definitive answers. They begin, instead, by learning to ask better, more beautiful questions. Thank you for joining this exploration into one of history's most enduring and captivating enigmas.